Estamos ao vivo no YouTube, pode começar, Mark.
Ok, obrigado, Larissa. Então, bom dia a todos. Estamos aqui para fazer a defesa do doutorado do João Gabriel Alencar Caribe, estudante meu de doutorado no CBPF. Tem membros da banca que não falam português, então vamos mudar para o inglês. So we'd like to thank all the members of the examining committee for partaking in the defense. I'll do it so traditionally we do it in the order from the furthest from CBPF to the closest. So we have Johan Zahn from Leipzig University, Sandra Fabri from University of Valencia, and George Matzes from UNESP in Sao Paulo, and Carlos Arro from UFRJ in Rio de Janeiro. So the way we'll proceed is João will give a presentation that will last between 40 and 50 minutes. And then we'll proceed to the questions from all the members of the examining committee in the same order from furthest to closest, if that's okay with everyone. Okay, so João, I think you can start whenever it suits you.
Okay, let me do it now. Okay, I started my clock. So good morning, everyone. Good morning from Brazil. I would like to thank you all for being here despite the different time zones. And I also would like to thank you all for accepting to be part of this committee. And I would like to thank the secretary for organizing all this. So thank you. My name is João. I'm a PhD candidate at the Brazilian Center for Research in Physics under the supervision of Professor Mark Casals. And today I'm presenting my work entitled Quantum Scalar Field Correlations in a Schwarzschild Spacetime. So as a little summary of what we are going to see, I'll begin with a very brief introduction, then I'll talk about generalities of the Whiteman function, and then start stating my results regarding correlations outside the horizon, correlations across the horizon, and a couple of interesting findings related to singularities that were in some sense hidden in the Whiteman function. And I'll finish by presenting my published work, which was about harvesting in Schwarzschild spacetime. So now, let me begin with a small introduction. So, our main motivation is that we want to better understand how correlations work on a quantum field on a Schwarzschild spacetime, specifically in 3+1 dimensions, because there we have a very rich geometric structure. We have orbiting nucleodesics, we have caustics, so we have a lot of things going on geometrically that could influence in a non-trivial way how correlations are distributed and how they work on that setup. And studying correlations is a thing of its own and is related to several different problems that are of interest. And for a couple of them, for instance, are the black hole information loss puzzle, which is related to correlations. Hawking radiation is also related to how correlations are distributed on throughout the space-time. And there is also the recent interest in entanglement harvesting, which also relates to correlations on a quantum field on a curved space-time. Well, there are many more examples, but these are the three ones that I'm showing here for a motivation. Now let me begin the actual introduction. So throughout this presentation, I'm going to use geometrized units where all fundamental constants of interest, the speed of light, Newton's constant, Planck's constant, and Boltzmann constant are set to 1. And we are working in the Schwarzschild spacetime. If you can see my pointer, I hope this is the case. Here on the right, we have a Penrose diagram representing the Schwarzschild spacetime. And for convenience and reference, I also wrote the expression for the Schwarzschild metric in Minkowski coordinates. Throughout, I will call the Schwarzschild radius R subscript S. On that spacetime, we employ the semi-classical framework to quantize a massless quantum scalar field. So the quantized field can be expanded as this. And here in this expansion, we have A and a dagger, which are the creation and annihilation operators, obeying the usual canonical commutation relations. The Uj is an element of a complete set of solutions to the Klein-Gordon equation. And the resulting vacuum of this quantization is given as usual as the state that is annihilated by our annihilation operators. Now, let us actually construct the quantum states that we are interested in. And for that, we have to construct a few complete sets of solutions to the Klein-Gordon equation. And for that end, and specifically thinking about our case, we will use this kind of solution to the Klein-Gordon equation. So availing the spherical symmetry of the Schwarzschild spacetime, we can take a solution and split it into spherical harmonics and a term that does not depend on the angular coordinates. This x perpendicular is meant to be understood as the coordinates that are not angular, that are not theta and phi, for instance. The normalization we adopt throughout is given by this expression. And now we define the actual field modes. So in region number 1, that is outside the horizon, the complete set of solutions is given by the ingoing and outgoing modes. The ingoing modes are modes of positive frequency with respect to the Eddington-Finkelstein V coordinate at scri minus. The outgoing modes are given by this boundary, these conditions, and they are positive frequency modes with respect to u at h minus at past horizon. In region number 3, that is on the so-called parallel universe, we also have a complete set of solutions which have this L to indicate that we are on the left wedge, which is another way to refer to region 3. And on the left wedge, we define modes like that. So there are ingoing and outgoing modes there as well, and they are defined by this condition. Inside the black hole, the complete set of solutions is given by Fr and Fl. Fr works as if it were an ingoing mode. It's a positive frequency mode with respect to the Eddington-Finkelstein V at h plus, the horizon of the right side. Fl works as if it was an outgoing mode. It is of positive frequency with respect to this barred u, which is the u coordinate inside the horizon, on the left horizon. Now, using these modes, we can write the Unruh modes, which are yet another complete set of solutions to the Klein-Gordon equation. We have 4 Unruh modes. 2 are the ingoing Unruh modes, and other 2 are the outgoing Unruh modes. These are positive frequency with respect to the Kruskal V coordinate on H+, and these are positive frequency modes with respect to the Kruskal U coordinate on H-. With using all these modes, we can define the 3 quantum states of interest by suitably using them, suitably combining them. So the Bohr state in region 1, which we are going to work with, is defined by the ingoing modes of the right wedge and the outgoing modes of the right wedge. The resulting vacuum is the Bohr state. By using the ingoing modes of the right and left wedges together with the outgoing modes, the Unruh outgoing modes, we define the Unruh vacuum in regions 1, union 2. And finally, the Hartle-Hawking state is defined by using all of the Unruh modes. And in principle, it should be well defined in the whole spacetime, but we will only be concerned with regions 1, union 2. So only with outside the horizon and inside the horizon in the physical universe. Now, just to summarize what we have done from a numerical perspective, we further decomposed all of the field modes by extracting the t-coordinate dependence and exposing the r-coordinate dependence. So these psi are what I'm calling radial field modes. These radial field modes obey a simple second-order differential equation that is tractable from a numerical perspective. And the boundary conditions of these radial field modes can be read off from the initial conditions for these radial field modes can be read off from the initial conditions for the F modes. And here on the right, we have the conditions defining the radial field modes and, of course, the scattering coefficients, the transmission and reflection coefficients. In short, our raw data set is composed by many solutions to the radial field modes, their derivatives, and the transmission coefficients. Now, let me talk a bit about the Weitman function. The Weitman function is defined as the field-field correlator, and in short, it encodes field correlations, of course, as it name points. It will be of importance for this presentation to keep in mind that the commutator of the field is the imaginary part of the Whiteman function. And that imaginary part of the Whiteman function can be written in terms of the retarded and advanced green functions. These two green functions are classical objects in the sense that they are fixed by the classical geometry of space-time. So the imaginary part of the Whiteman function is, in that sense, determined by the classical geometry and not by the quantum state itself. On the other hand, the real part of the Whiteman function, which is related to the anti-commutator, is what carries state dependence. Now, to talk about the singularity structure of the Whiteman function, I have to introduce three ingredients. The first one is the notion of normal neighborhood. Rigorously, a normal neighborhood of a root point x is a region such that every other point within this region is connected to the root point by a unique geodesic which is completely enclosed within the normal neighborhood. Another ingredient is Singh's word function, which is 1/2 of the square of the geodesic distance joining x and x prime. Now, Singh's word function, as defined here, is well defined inside the normal neighborhood of the root point x. However, it has been shown in this work by Casals and Nolan that one can suitably construct an extension of Singh's word function beyond that normal neighborhood. That extension is, of course, not unique. Using these three ingredients, we can understand the singularity structure of the Whiteman function. So when we have let me call this x prime the varying point, and x the root point. When you have the varying point inside the normal neighborhood of the root point, the Whiteman function behaves in this way. What is to be understood here is that this capital U and capital V are real-valued B scalars, which are completely fixed by the geometry of the spacetime, while the state dependence is encoded in this real-valued B scalar here. So this real-valued B scalar encodes state dependence when we have the varying point inside the normal neighborhood of the root point. And here we have this delta capital T, which is a difference between two global time functions. So this isn't the usual coordinate time by no means. When we have the varying point beyond the normal neighborhood, we know that the Whiteman function still presents singularities. Here it had a log of sigma singularity, so whenever sigma is equals to 0, it has a singularity, and here we have a PV-like singularity. Now, beyond the normal neighborhood, we still have singularities happening whenever the 2 points, the root point and the varying point, are connected by a new geodesic. But there are two distinct situations. So when these 2 points are not, when the varying point is not on a caustic point, the singularity structure goes like that. Now let me briefly explain this to you. So on the figure on the right, we have several orbiting new geodesics. How to understand the singularity structure using this figure? So it goes as follows. The root point here is estimated to be x, and the varying point, x primed right here. The red curve, they join these 2 points. However, it joins the 2 points before completing a half orbit around the horizon. So the singularity that we expect here in the real part of the Whiteman function is a PV, and in the imaginary part, a minus delta. The green curve, on the other hand, it connects the root point with the varying point after completing a half orbit. Then the singularity that we expect in this case, in the real part, is a minus delta, in the imaginary part, minus PV, and so on. So the logic follows. When we have the varying point on caustics, instead of a 4-fold singularity structure, we know that there is a 2-fold singularity structure in the retarded green function. In this work, we show that this is the case in the real part of the Whiteman function as well. Now, I will briefly present to you the expressions for the Whiteman function that we are going to use. So when both points are outside the horizon, we can write the Whiteman function for the Bower, Unruh, and Hartle-Hawking states in terms of the modes that we have data for, as presented here. This isn't something new. This was already presented by Candelas in the 80s. And these expressions aren't particularly insightful in this way that they are posed. Now, when we have the root point inside the horizon and the varying point outside the horizon, the expressions written in terms of the radial modes that we have looks like that. And this is, to the best of our knowledge, a new expression that was not published before. I would like to call your attention in this expression to the fact that we have this term, real part of this combination of factors, in the Uru state Weidmann function. And we also have the real part of the same combination of terms in the Hartle-Hawking state Weidmann function. So they share a common term, and I would like you to keep that in mind. Now let me present my first results regarding correlations outside the horizon. So the first one is the singularity structure on caustics. So what we have done is as follows. We took the root point x, fixed it at r approximately 6m, say. We also fixed the x primed at the same radial coordinate, and they are separated by an angle of pi, so that x prime will lie on several caustic points that are going to form in this position. Using this setup, we paired x with the several x primed and produced a plot of the Weidmann function for the Bower state. And here we are showing the real part of that Weidmann function. As can be seen on the left in this log plot, there are 1, 2, 3, 4 singularities that are visible here, which are the expected singularities that appear whenever a caustic point forms on x primed. In the first singularity, we have this shape, this functional form. In the second singularity, we have this functional form. And then for the third singularity, we have the same functional form as we had for the first. And this is expected. This is the twofold structure that was known to happen for the retarded green function. The same kind of work has been done for the retarded green function in Zengino, and Galley, but they only have done the retarded green function. To the best of our knowledge, this is the first time someone is doing this kind of study for the real part of the Weidmann function. And while here we are using the Bower state, this is straightforward to reproduce for the Uru and Hartle-Hawking states as well. And this is our first new result. Now let me go to our second new finding. And this one has a more involved setup. Here we fix the root point x right here, this purple dot, at r approximately 6 again. And then Barayed covered a lot of the outside region with these orange dots, which are all separated by an angle of pi over 3 from the root point. Using this setup, we computed the Weidmann functions for the 3 quantum states. And then we evaluated what we call the quantum relative difference, which is the difference between a given quantum state and the Weidmann function for a given quantum state and that for the Bower state. And here is the results that we obtained. Now, on the left, we have the quantum relative contributions for the Hartle-Hawking state, on the right for the Uru state. There is a lot to be seen here, so let me explain it to you calmly. In both plots, the top thick dashed line is r approximately 2.1, which is the closer to the horizon from the outside that we have data for. The bottom thick dashed line is r prime approximately 20m, which is the furthest from the horizon we have data for. The thin diagonal line that you can see here in between the two thick diagonal lines is the photon sphere r equals to 3m. And these blue curves here, the blue dashed lines, they have a special meaning. So let me explain to you. For instance, let's use this one, which is labeled as 1. What are these points? So this line, it represents the points x primed that are connected to the root point x by a new geodesic that completes 1/2 orbit before connecting them. The two blue dashed line is the same thing, but after completing 2 half orbits, 3 half orbits, 4 half orbits, and so on. Here to the future of the purple, below to the past of the root point, the purple point. So this is what you are seeing, and this kind of plot will be recurrent throughout this presentation. So try to keep that in mind as much as possible. Now, what can we see here? We spotted a local maximum in the quantum relative contribution for the Hartle-Hawking state that tracks very closely the line of delta t coordinate time equals to 0. So this brown line is actually drawn along the local maximum. However, we can trace that line with the line of delta t equals to 0. And this is something interesting to notice. Now for the Uru state, we also had the local maximum, but here that local maximum seems to travel from some value of u primed, the u coordinate of the varying point, that we do not actually understand how to set. And then it seems to asymptote towards a constant value of that u primed coordinate, which we verified to be approximately the u coordinate of the root point, minus 14.8. The difference between these two behaviors might be related to Hawking radiation, because the difference between the Hartle-Hawking state and the Unruh state is that the Unruh state contains Hawking radiation, while the Hartle-Hawking state only represents a black hole in thermal equilibrium with its environment. So the difference between these two is Hawking radiation. So we suspect that there is a relation between Hawking radiation and what we see here. Now let me go to correlations across the horizon, which I believe are the most interesting results, or the most exciting, I'd say, results we have. And for this we have done the following setup. We fixed the point inside the horizon at 0.76, which was the closer to the singularity we had data for. And then the outside point was fixed at a given value of r coordinate, and we varied its v coordinate. Again, the orange dots are separated from the purple dot by an angle of pi/3. On the right, we see the results. So on the right, we see plots of the Whiteman function for the Unruh and Hartle-Hawking states. The one for the Unruh is the red, for the Hartle-Hawking is the dashed green. So we see a local minimum close to the horizon. And as we move further from the horizon, we see that this local minimum moved to a larger value of v primed. And as we move further, we see that the local minimum moved even further from the horizon. So there is at least a local minimum that is visible here that seems to emerge from the near horizon region and moves away from the horizon as v primed increases. Now, we are able to notice something. Remember that when I told you that the Whiteman function for the Hartle-Hawking and Unruh states in this setup, they share the common term. So now I'm defining this common term as W delta to study that in a deeper sense. And we wondered what would happen with these Whiteman functions if we subtract this common term from them. So we subtracted W delta from WH and WU. The results are on the right. So as can be noticed, there is still a local minimum in the red curve for the Unruh state. However, the Hartle-Hawking state completely lost this local minimum, and that local minimum for the Unruh state, it seems to be getting wider and not exactly propagating as it was before. So we find that this is a strong evidence that W delta, the common term, is responsible for producing the local minimum that was moving away from the horizon that we have just seen in the previous plot. Then why not study it in an Eddington-Finkelstein diagram, a more comprehensive study of that term? So what we have done here was to fix the root point inside the horizon. Of course, I can't draw it here because this is valued only outside the horizon, these coordinates. And then we vary the outside point throughout the region outside the horizon. And here we see a plot of W delta on that set of points. As can be noticed, we have a clear transition from positive values to negative values, which is sharply localized. The 0 is sharply localized, close to u primed equals to minus u. So this condition is close to tracking the green dots, which is something to keep an eye on again. Now, in order to understand that term even better, we took cuts of the previous plot by selecting surfaces of constant r of the previous plot and showing them like that, so that we can take a look at the functional form of whatever is happening there. And here we see the results. So the red lines are for r equals to 2 plus 1, 2.1, close to the horizon. Green line, r equals to 2.5. Blue line, 6. Orange line, 10. Purple line, 20. So from the green to the purple, we are moving away from the horizon in both top and bottom plots. Let's begin with the top plot. We clearly see that there is some kind of step-ish behavior. So we have almost some value that is close to being constant here, some value that's close to being constant here in a step-like transition. However, it is also followed by a local minimum. So we have a step-like structure, a structure composed by a step-like behavior and a local minimum, and we can clearly see it here. As we move away from the horizon, the whole structure is dwindling. So the step is becoming smaller and the local minimum less visible. However, we noticed that there is a global factor in W delta. That global factor is this R times R prime to minus 1. Maybe this is responsible for producing the dwindle, maybe not. To test, we multiplied W delta by that factor to eliminate this global term, this global factor. The result can be seen here, and now we can see that there is some dwindling happening. The height of the step close to the horizon is larger than the height of the step away from the horizon, but that dwindling seems to be accommodating. So it dwindles, say, until like 6m, but after that, there isn't much more dwindling happening in the step. And at the same time, as we move further from the horizon, we can have a better look at the local minimum. So the local minimum becomes more pronounced with increasing R. Heuristically, we were able to understand what is actually encoded in that term, and it becomes clearer by rewriting it instead of using the expression in terms of the radial mode, by using the expression in terms of the Eddington-Finkelstein modes. So this term encodes correlations across the horizon because it is composed by the upgoing terms outside the horizon and the upgoing terms inside the horizon. So this term is 0 inside the horizon, while this one is 0 outside. So it is definitely encoding correlations across the horizon. More than that, the prescription we use to define the L-wedge modes selects that U prime equals to minus U as a special position. Here it's important to remark that this is written in terms of the Kruskal U coordinate, but if we write it in terms of the Eddington-Finkelstein U coordinate, the relation still holds. Now, we also can note that there is a shine term in W delta, and this shine term might be responsible for filtering out larger frequencies, in the sense that we believe, but we don't have exactly a proof, that the low frequency modes are the one responsible for the step-like plus local minimum in W delta. If we confirm this to be the case, then we might associate the dwindling to the effect of the potential barrier, which in fact acts much more on the low frequency modes than on the large frequency modes. We wonder if that step-like structure is related to Hawking radiation in some sense, because it's clearly encoding correlations across the horizon, and it appears for both Unruh and Hartle-Hawking states. And we know that in 1 plus 1 dimension, 1 plus 1D Schwarzschild, the Whiteman function presents no peak. So there is nothing like what we are seeing here in the Whiteman function in 1 plus 1D. But in 1 plus 1D, the derivatives of the Whiteman function are known to show a peak, which is related to correlations across the horizon. So maybe what we see is something similar of the same nature that is still to be determined. Now, while performing this exploration, we found a couple of interesting things regarding singularities in the ingoing and outgoing sectors of the Whiteman function. So the idea is that we can take the full expression of the Whiteman function and separate it in 2 sectors, one that we call the ingoing sector and another that we call the outgoing sector. The ingoing sector contains all of the initially ingoing modes, and the outgoing sector contains all of the initially outgoing modes. For the Bower state, this split is performed like that. So we define the ingoing sector as W in, small case, the outgoing sector as W up, small case. Also, it's important to remark that now we are working with both points outside the horizon. The ingoing sector, as can be seen here, it contains only the initially ingoing modes, so it contains only ingoing modes. The outgoing sector contains only outgoing modes, as pointed here. For the Unruh state, we split the Whiteman function like that. So the Unruh state shares the ingoing sector with the Bower state, but it has a different outgoing sector. And here I call this capital up for the outgoing sector, because the outgoing sector for the Unruh state is given in terms of the outgoing Unruh modes and not the Eddington-Finkelstein modes. It looks like that. Finally, for the Hartle-Hawking state, the ingoing sector is different from the one from the Unruh state. It's given in terms of the ingoing Unruh modes and is written like that when we write the Unruh modes in terms of the Eddington-Finkelstein modes. However, the outgoing sector for the Hartle-Hawking state is the same as that for the Unruh state. Now, okay, what have we found regarding these ingoing and outgoing sectors? Here we can see what happens. So let me explain what's going on. We took the root point and fixed it at r approximately 6. So I placed a small purple dot on the position of the root point, which is separated by an angle of pi/3 from the varying points. The varying points are also outside the horizon. So this is the setup here. The plots looks like the ones that I shown before. So thick dashed line of the top is for r prime approximately 2.1, thick dashed line below r prime approximately 20, photon sphere thin diagonal dashed line, and here we have these lines representing points connected to the purple dot by orbiting no geodesics. This is the structure of the plot on the left and on the right. So the same thing as we have seen before. On the left, we see the upgoing sector of the Whiteman function for the Bower state. On the right, we see the ingoing sector for the Whiteman function of the same state, of the Bower state. Now let's see a couple of things here. If we follow the blue dashed lines, where we expect singularities to happen, we see in the ingoing sector that the singularities do appear. We see a slightly bright curve below the n equals 5, a slightly bright curve below the n equals 4, n equals 3, 2, 1, and 0. For 1 and 0, it is especially visible. So to the future of the purple dot, we see the light crossing singularities in the ingoing sector. Now look at the outgoing sector. To the future of the purple dot, these blue dashed lines, they are not tracking any kind of singularity. So these light crossing singularities in the future of the purple dot are missing in the outgoing sector. Now, to the past of the purple dot, to the past of the fixed point, we see that the blue dashed lines, they trace the light crossing singularities, but only down to the photon sphere. This portion of the blue dashed line, the portion below the photon sphere, for instance, isn't tracking anything. However, when we look at the upgoing sector, the behavior is the opposite. To the past of the purple, we see that out of the photon sphere, so in this region, the blue dashed line is tracking anything. However, below the photon sphere, it is tracking now the light crossing singularity we expect. We can see a zoom in the insets just to clearly show that we are tracking the singularity below the photon sphere to the past of the purple dot. What we are seeing here then is a complementary behavior. The light crossing singularities that the ingoing sector has, the outgoing sector misses. And the light crossing singularities the outgoing sector has, the ingoing sector misses. On top of that, the outgoing sector is especially easy for that end. We can see many local maxima, for instance, here, here, and here, which are completely unanticipated. We are not expecting them to appear. They are very visible on the upgoing sector because, well, it misses many of the light crossing singularities. However, we can still see them, although not as clearly as in the upgoing sector, in the ingoing sector. Since it's not that easy to see in the ingoing sector, I encircled this unexpected local maxima in green for the ingoing sector. So these green shapes are encircling the unexpected local maximum in this term. In short, the unexpected local maxima appear in both sectors. And when we sum both terms to complete the Whiteman function, they cancel. So this is an interesting behavior. Now I would like to take a better look at what are these local maximas. And for that, I took a cut of r equals to r prime equals to 6. So now we are looking at the surface of r equals constant of the previous plot, especially at the r equals constant equals to 6. What we see here is a plot containing the full Whiteman function, dashed green, blue outgoing sector, red ingoing sector. And we can notice that whenever there is a light crossing singularity, which shows in the green dashed line, it overlaps almost exactly with the red line. So the light crossing singularities in this situation are dominated by the ingoing sector. On the other hand, there are no light crossing singularities that can be seen in the outgoing sector. We conjecture then that these local maxima we have spotted are also some smoothed version of singularities. Because if we look here, for instance, in this local maxima in the blue curve and this singularity, we see that, well, the local maxima is much smaller than the non-singularity, but in terms of orders of magnitude, it's roughly a single order of magnitude smaller, so it's not that smaller. And there are more arguments that complete this conjecture that you're going to see in a couple of seconds. Similarly, considerations also hold for the imaginary parts. So now, in order to get a better glimpse of what are these unexpected local maxima, we use the upgoing sector. So here we see in blue the imaginary part of the upgoing sector, in red the real part of the upgoing sector. And below we can see what these singularities, what these conjectured singularities actually look like. You can notice that each singularity contains a local maximum and a local minimum. It might be difficult to spot, as in this first blue one, but it's here, it's there. On top of that, the interval, the delta V interval between two successive even or odd of these non-light crossing singularities is closely approximated by the period of an orbit in geodesic. And this is something to keep in mind because there might be a connection, although we are not able to completely determine that. We also found that this qualitative model can describe, in some sense, the features that we see. It has a local maximum, local minima, and a roughly similar shape in some sense. So we can state the singularity structure in terms of this qualitative model, which I have done, hoping that this is easier to understand. Regarding the light crossing singularities, there is an interesting thing we can see also. Now we are talking about the expected light crossing singularities. Here we see a cut where both the root and the varying point are at the same radial coordinate, 2.1, below the photosphere. As you can see in this plot, the green dashed line, it overlaps with the blue line on the light crossing singularities. This means that the light crossing singularities are dominated by the upgoing sector when both points are below the photosphere. As we move closer to the photosphere, so we use a point that is very close to the photosphere, we see that on the light crossing singularities, there is no dominance. So the ingoing and upgoing sectors seem to provide roughly the same contribution to the light crossing singularities. And above the photosphere, what we see is that now the ingoing sector is dominating the light crossing singularities. So in short, we can state that a light crossing singularity will appear in the ingoing sector, for instance, of the Whiteman function if the 2 points, the root and the varying point, are connected by an ingoing geodesic. Conversely, a light crossing singularity will appear in the outgoing sector if the 2 points are connected by an outgoing geodesic. And this explains, well, why they are missing in some cases and not in other cases. Now I'm going to present you my published work, which is about entanglement harvesting near Schwarzschild black holes. In short, what is entanglement harvesting? So given two quantum systems, A and B, they can become entangled in two ways, essentially. The first one is by communicating with one another through the background field, that is, by signaling from one another. And the second one is by extracting pre-existing entanglement from the background field. The second way of becoming entangled is what we call entanglement harvesting. Regarding that effect, we know that in a flat spacetime, when we have two timeline connected detectors, the entanglement they acquired is always dominated by communication and not by harvesting. Then we wonder if this is also the case for a Schwarzschild background spacetime. For that, we prepare a setup that goes as follows. We consider two point-like two-level systems, A and B, which are Unruh-DeWitt detectors, and they are coupled to the background field by this Hamiltonian. Here, lambda is the coupling constant, eta is the switching function, which tells how the detectors turns on and off, tau is the proper time, mu is the monopole operator, and x is the word line of the detector. And of course, this capital omega that appears in the monopole operator is the energy gap separating the ground state from the first excited state. For our experiment, we placed one of the detectors at this point, the detector A, and it's fixed at that point at a given radial coordinate. Detector B is also placed at the same radial coordinate, but it is separated from detector A by an angle gamma that we are going to vary. On top of that, the switching functions for both detectors are Gaussians that are centered on a given t0. And the width of the Gaussian is this capital T, which tells us for how long they keep interacting with the background field. Regarding the experiment, what we do is as follows. We begin by preparing a quantum state where both detectors are in their ground states, so they are not entangled. And the quantum field is in one of the three vacuum states, Unruh, Bohr, Hartle-Hawking. Then we time evolve the complete system until t going to infinity, which is what we call the final state, and we get rho infinity. To understand how the detectors are entangled, we trace over the field to obtain the density matrix describing the joint state of the detectors. And to quantify the entanglement, we calculate the entanglement negativity. In this setup, the negativity is given by a difference of two terms, m and l. M is a term containing, is a non-local term because it depends on the histories of both detectors through their word lines, for instance. Here we have XB and XA. The noise term L, it depends only on a single detector because here we have LDD. So when we change this D prime by D, we will only depend on the history of a single detector. Essentially, this noise term is a transition probability of the detector. So it's independent of the history of the other. In order to distinguish harvesting from communication, we use this kind of criteria. So we take m psi, the non-local term, and write it as a sum of two terms, m plus and m minus. M minus is the non-local term m, but evaluated with the imaginary part of the Whiteman function instead of using the complete Whiteman function. M plus is the non-local term evaluated with the real part of the Whiteman function instead of the complete Whiteman function. In short, M plus should encode state-dependent entanglement, while M minus should encode state-independent entanglement, because the imaginary part of the white one should be state-independent, and the real part of the white one carries state dependence. Then the criteria goes as follows. When M is dominated by M plus, we can say that A and B acquire entanglement mostly by harvesting. Conversely, when the non-local term is dominated by M minus, we can say that they acquire entanglement mostly by communicating through the background field instead of by harvesting. And now I'm going to present my results. So let me take some time to explain this to you. On the left, we see an animation. The red dot is the detector A. This blue line here emanating from detector A is its light cone. So we are seeing the light cone propagating from detector A. The black circle is the black disk, is the black hole, and this black circle is the R coordinate of both detectors, and detector B is placed all around this circle. On the right, we see plots of the non-local term M, M plus, M minus, and the local term L as a function of gamma. So when we place detector B in this position, say gamma equals pi over 2, then we should look at this point. And so the logic goes. As we know, there is a singularity whenever the 2 points are connected by an geodesic. So whenever the light cone intersects the radial coordinate of detector B, we expect a singularity in the Whiteman. And this is reflected here. The singularity in the Whiteman reflects as these peaks in the non-local term. So these peaks are following the intersection of the light cone with the R coordinate of detector B. And as can be seen, when we are close to that peak in this situation that we are seeing here, the M term is almost completely given by M minus, while M plus is very close to 0. Now I will play the animation for a couple more time, and I want you to notice that there is something non-trivial that will happen as soon as the caustic point forms. So this is right before the caustic point forming on the radial position of detector B. And here we can see that M is clearly and almost completely given by M minus, but then slightly after the caustic point forms, we have a different behavior. Here we have M almost completely given by M plus, while M minus is very small. So what we are seeing here is a situation where detectors A and B are time-like connected to one another, and entanglement is dominated by M plus, thus entanglement is mostly harvested from the background field, in contrast to the situation of flat spacetime that I have pointed previously. And so the situation goes, but now entanglement is too weak and the non-local term cannot overcome the noise term anymore, so the entanglement as quantified by the negativity is 0 past that point. For this situation, we used the Bower state, but the results are similar for the other two quantum states as well. So in short, we have shown that harvesting is possible for time-like connected detectors, and it's dominated and it dominates slightly after the caustic point. We can observe this effect even when detectors are placed very close to the horizon, but in this situation, they must have enough proper time to interact with the field. So we have to adjust the switching width as we move closer to the horizon in order to observe this effect. We can understand it in terms of the fourfold singularity of the Whiteman function, because as soon as the caustic point forms, the singularity in the Whiteman function changes. So the strong delta singularity that was in the imaginary part of the Whiteman moves to the real part of the Whiteman. And the weak PV singularity that was in the real part moves to the imaginary part. So the real part now diverges in a stronger way than the imaginary part, which allows M plus to be much larger than M minus slightly after a caustic point. To the best of our knowledge, this is the first work to explore harvesting in Schwarzschild, and here we mean Schwarzschild 3+1D. Now I'm going to make my final considerations. So we tested and used a method to compute the Whiteman function for a massless scalar field on a Schwarzschild spacetime, and it is a particularly efficient method because we can do calculations in a matter of hours. So a different setup only takes a couple hours to test or to explore. For the first time, we revealed the singularity structure in the real part of the Whiteman function on caustics. And we found peaks in the Whiteman function for the Unruh and Hartle-Hawking states when both points are outside the horizon. And we wonder if there is a relation between these peaks and Hawking radiation. For points across the horizon, we found that interesting structure composed by a step-like behavior followed by a local minimum that moves away from the horizon as time increases. Time here is in a loose sense. And we also found unanticipated non-light crossing singularities in the ingoing and upgoing sectors of the Whiteman function. And we also shown that they follow a fourfold singularity structure. Finally, we also perceived that the light crossing singularities in the ingoing and upgoing sectors separately, they depend in a non-trivial way on the arc coordinate of the points being considered. This is what we have seen when looking at these results. And finally, we have shown that in the Schwarzschild spacetime, entanglement acquired by two time-like connected detectors can be dominated by harvesting. The detectors just have to be aligned slightly after a caustic point. Now, for future perspectives, of course, I want to keep exploring to uncover and to better understand our results, so to completely and comprehensively be able to understand all of them. We also want to explore correlations inside the horizon. We already have data for this exploration. We just have to perform that. We think it will be also interesting to repeat the study of the Whiteman function, 2 points outside, 1 point inside, 1 outside, but with the derivatives of the Whiteman function, because this will allow us to compare the results directly with the literature on 1+1D Schwarzschild at least. We also find it interesting to work with the response function of a freely falling Unruh detector slightly after it crosses the horizon, because there seems to be a non-trivial behavior happening, and we might be able to dig deeper than the literature currently does. We also, in a bolder proposal, we could also try to take the Whiteman function at filter no infinity and evolve it back, ignoring whatever fell into the horizon, in a way that we might try to understand how well an observer that is able to capture everything that do not fall inside the horizon, how well that observer is able to recover the initial data, and how well that observer describes what happens. And finally, we can explore harvesting across the horizon in 3+1D Schwarzschild. This has only been done in 1+1D. And this was my presentation. I'd like to thank everyone again for your attention, for being here, for accepting to be part of the jury. Well, thank you a lot. So that was it.
Thank you very much, João, particularly for sticking to the time.
Yeah.
So we'll proceed now to the questions from the examining committee. So unless there's any objections, in principle, we'll follow the order that I said earlier on, which is the traditional one in CBPF, which is the furthest. I know it's an online meeting, but still the person who's furthest from Rio de Janeiro to the closest one. So if that's okay, then we'll start with Johan. So you can start whenever you wish, Johan.
Yeah, okay. Yeah, thanks a lot for the nice presentation. So I suppose I ask questions. Let me begin by asking questions on your presentation. So if you go to the start, not quite the start, but rather at the beginning.
This is the beginning of the results. Is this?
Yeah, a bit more to the start yet. I think page 6, I think. So let's begin with something very simple here. So what is this scalar product that you have written down here?
Oh, the scalar product is the usual Klein-Gordon linear product that we define using the Klein-Gordon current.
So it's evaluated how?
Well, you take the integral of the Klein-Gordon current on some Cauchy surface, and that's it in simple terms.
Yeah. Okay. Fine. Then on the next page, I was wondering why you include the in-L modes in the definition of the Unruh state. I mean, as far as I understand, the in-L modes, they only appear in region 3, whereas your Unruh state should only be defined in region 1 and 2. So isn't that just superfluous?
What we see happening was that the L modes, just give me a second. Inside the horizon, we have a contribution coming from the. You're right, Jochen. You're right. I made this confusion because the upgoing L mode, it plays a role when we look at points inside the horizon, but not the ingoing L modes. So they are superfluous for our purpose here. You're right.
Okay, well, that is good to know. On page 10, this is just regarding notation, but there you have G ret and G advanced with a psi. What does the psi stand for here?
No, the psi is a typo. It's a clear typo. I apologize.
Okay, fine. Then, okay, I don't remember exactly on what page that was, but I think on perhaps the first time you really presented plots, or well, not really the first time. Perhaps you go a bit, yeah, and a bit further. Yeah, that's fine. That's fine. Next page, perhaps. Yeah, next page. And again, next page. Yeah, here, I think it was here.
Mm-hmm.
Here at some point, as far as I understood, you said something like looking at these plots here, you were saying moving further away from the horizon by looking at, well, one single plot here. But I don't quite understand what that means because all these plots are at fixed values of R prime. So what do you mean by going to the right here, indicating going further away from the horizon?
Well, see, well, let me see. I believe that I included versions of these plots on an Eddington-Finkelstein diagram, and then with respect to that diagram, these plots are sections. So let me see, like this one. So we can cut diagonal lines here on this plot, for instance.
Don't
we
see which, yeah, okay.
So say that we cut a diagonal line at r equals to 2.1. So this is the first plot. Now we can do the same kind of thing with a diagonal line, say at 10 and then at 20.
Yes.
So what we see, so what we are seeing here is the behavior, say, of that brownish thing, of that brown line. But here we are talking about points across the horizon. So I'm using the plot as a reference only. So what I'm doing is I have a map of the complete Weitman function, and I take cuts of constant r, and then I move these cuts outside the horizon, trying to make some sort of tomography of what's happening. And what we see in that tomography is that there is a local minimum that seems to be moving towards larger values of r.
Well, but it's not moving. I mean, I don't understand that statement. What do you mean now? I mean, in one plot, it's a larger value of v prime, or v if you want.
Yeah, so
But
this
r is fixed.
Yeah, but what I mean is that this local minimum, which was at v equals 20 when r were 2.1, is now at v equals 40 when r equals 10, and then it goes to v equals 60 when r equals 20.
Yes.
And I assume the logic then follows, because I don't have data for larger values of r or smaller values of r outside horizon. So this is what I mean by moving.
Okay. And is this a kind of a, I mean, what is the, if you want, velocity of this? Does it correspond somehow to a radial null geodesic, this kind of trajectory, or?
I don't know. Well, we can say the following. So may I move a couple plots further to explain that?
Mm-hmm.
When we managed to isolate this behavior that we see here, what produces the local minimum, which is the W delta term, the so-called W delta.
Yeah.
And here we can see what seems to be happening. Well, it seems I don't have enough, say, testing to say that it is, but I can say that it looks like it is moving on this new geodesic.
Okay.
Which is
good. That's fine then.
But please take that as I mean, it seems to be. I'm not saying it is. I have strong evidence that it is or anything. It needs to be deeper explored.
So okay. So there are indications that you have a structure which is moving outwards, so to say, or upwards. That's the correct terminology, I suppose, in this context. Okay. Page 23. Now here I'm puzzled again by the statement in the third line. You have your expression for these correlations. You pick out one particular term out of this expression, and then you say this particular term encodes correlations across the horizon. So does this mean that the other terms do not encode correlations?
No. This statement is only about this term. The other terms, they also, I believe they also include correlations as well. I roll back to see, but the logic would be whenever you have x, the root point in this setup, you are doing things inside the horizon. Whenever you have x prime, you do things outside the horizon.
Sure.
What I mean is that this combination of terms is is particularly appealing because the upgoing term, it is 0 inside the horizon. I mean, it has 0 initial data inside the horizon, while the upgoing L term has initial data inside, but 0 initial data outside. So in that sense, I say that it must be encoding correlations across because of that. And it's explicitly doing so. The other terms might also encode these correlations as well. There is nothing wrong with
What
them
do you
doing
mean
that.
by might? I don't understand this. So are these other terms correlations or not?
Okay, may I go back to the expression, to the full expression, to look at this issue? Or not?
I mean, what would be the criterion? I mean, it's a two-point function. So how do you determine whether it encodes correlations or not?
Well, a two-point function always encodes correlations. My point here is that W delta, it is a combination of terms such that one is 0 inside the horizon and the other one is 0 outside the horizon. Now, for the other terms, we could have, for instance, I believe we have combinations of the ingoing term, for instance, F in. The ingoing mode, it isn't 0 inside the horizon.
Okay.
So in that sense, the terms including the ingoing mode also encodes correlations across the horizon, but not, I would say, in a different way than W delta, because W delta is a combination of two terms where one is 0 inside and one is 0 outside. It is different from a combination of terms involving the ingoing modes, which are not 0 inside the horizon. This is why I call attention to this particular term. But in the end, of course, everything is encoding correlations across. My statement here...
Okay, so that's what I would hope, honestly, yes. Okay, let's continue on page 36.
Yep.
I'm a bit puzzled, honestly, by this distinction 1 and 2. So perhaps you can explain a bit more in detail how you distinguish the two, or perhaps what communication through a background field is supposed to mean.
Well, what do I mean by communication? Say that we have two detectors A and B. They don't interact with... Okay, they interact only with the background field. They don't have, say, a Hamiltonian that directly couples both of them.
Yeah.
So what you can do, for instance, is you can try to use detector A, make it communicate with the background field. It will send a signal through the background field that will propagate on that field, and that signal then can reach detector B.
Yes.
When this happens, we say that detectors are communicating through the background field. It is in that sense that I mean communication. So
what kind of communication is this? I mean, this background field, could it be a classical field?
This background field could be a classical field, sure. The classical field would allow for communication between two systems.
Yeah.
However, a classical field would not allow, I don't see straightforwardly how a classical field would allow, for instance, for harvesting.
But could it produce entanglement?
Sure, it could produce entanglement, but that entanglement should be associated to communication mostly.
Uh-huh. No, I mean, I know next to nothing about quantum information, but one thing I seem to remember is that there is this class LOCC of operations, local operations and classical communication. And
Sure,
there is one of the main theorems of quantum information theory is that with these kind of operations, you can never produce entanglement. Seemed to
sure.
me at odds with what you just said. Because you
Well,
have local operations at your two detectors and you communicate via a classical field. So does your setup, do you have so to say, disproven this quantum information theoretical statement?
no, I don't. I don't think I have disproven it. All I'm stating is that we have a background field. In this case, in my setup, it is a quantum field, and you can send
Yes.
and you can send signals.
Yes, but my question was, could you also do it with a classical field? And you said yes.
Well, in a specific sense, because say that okay, a classical field will have this. The imaginary part of the Whiteman function for a quantum field is the retarded ring function and the advanced ring function, essentially, which are classical structures, right? So these are shared with a classical field. My point is that communication here in this setup is ruled by the imaginary part of the Whiteman function. So in that sense, we can use these classical structures to produce communication between the two detectors. And this succession of communications might end up entangling both detectors.
But you're using a quantum field.
Yes, I'm using a quantum field.
Okay, so do you still stick to your claim that you could replace it by a classical field?
No. No, I
Yeah,
don't.
better not. I mean, I think honestly, I think this distinction is completely irrelevant, honestly, because you see the commutator is a quantum object because it's a commutator. There's an H bar in it. So calling that classical is just bad terminology, I think. So
I s-
honestly, I think this distinction does not make any sense. But okay, that's my point of view. But
No, actually, I'm not inventing any of this. So there are references. I'm
yeah, I
following
know that there are
references
references,
in
but that doesn't
harvesting.
mean that they make sense. But okay,
I'm,
at
I'm
least not
just
to me. Okay.
I'm just building up on the existing references. So this is all I'm doing. I'm not setting new things.
Yes, of course. But I mean, for a PhD thesis, you would expect that you understand what is the logic behind what you are doing. Yes, and I think it is important that what you call communication here is really still communication with a quantum field. So you're exploiting the quantum field structure. Another question, is the entanglement produced by what you call communication is worth less than the one produced by harvesting?
So you are asking me if the
I mean,
entanglement
why do you distinguish the two? Is one worse than the other, or worth more than the other, or?
well, if one is more than the other, as I presented in the small video, it depends on how the detectors are placed in the space-time.
Yeah,
So
no, but I mean, in the end, you just want to have entanglement. Does it matter where it comes from?
sure. So the idea of what I understood is that the idea that of separating communication from harvesting is that harvesting is related to the existing correlations in the background quantum field. So if you are able to study, you would be able to use this harvesting phenomena as a probe of pre-existing correlations of the background field, and this might allow someone to gain insights about how correlations are distributed and how they would interfere with experiments that happen on that field.
But you say the entanglement produced by communication is not due to pre-existing correlations in your quantum field?
Okay, to leading to what we know is that, well, and this relates to this splitting here. So this splitting is based on a paper entitled When Entanglement Harvesting Isn't Really Harvesting, and this deals, I believe, with this question.
I read this paper. I mean, you don't.
And
but I mean, I'm just asking, yeah, because you said you emphasized this point that if you get entanglement by what you call harvesting, then this is due to the correlations present in your quantum field. So I would like to know, does that not also apply to the entanglement produced by communication?
Okay, so I don't know the answer in the general case, but I know the answer for the leading order perturbation, which is what we are doing here. So to leading order in perturbation theory, this term is assumed to be encoding entanglement due to harvesting, because to leading order in perturbation theory, according to that paper, the sequence of interactions with the background field that would allow for communication is actually given by the commutator and not the anti-commutator. So it should not be, it will not appear in the M plus term. So this would be the logic behind the assumption that M plus to leading order should encode harvested entanglement and not communication mediated entanglement.
Okay, this still doesn't answer my question.
So your question is about if I can harvest entanglement, that is?
No, my question was, is the entanglement produced in your terminology by communication not due to correlations present in the quantum field?
Well, to leading order, leading order, the commutation only plays a role in communication between the two detectors. So this is the reason for me to assume that the commutator, or M minus, would not encode harvesting and harvesting as well. But I recognize that the whole argument, both mine and the references arguments, they should be explored deeper. And even Mark pointed me that he had his doubts about the arguments presented there.
Yeah. Okay. Well, perhaps then we stop here at this point, and then perhaps just on your last slide.
These last or the last?
Yeah, the very last one, I think. The next to last point. So I'm not quite sure what you mean by that. Evolve the Whiteman function from future null infinity back to the initial data surface. What is precisely meant by that?
Okay, this is a bold proposal which might need to be tweaked, but the idea would be, say that you are someone that is able to collect everything that doesn't fall down the horizon. So you're able to collect all the information that arrives at future no infinity, and you are that someone. Then I wonder how well that someone can describe the initial state, because in principle we should be able to use the data he collected at Scriplus as some sort of initial data and try to understand how the field looks in the bulk of the space-time, for instance, in order to understand how he would tell us the history about what was happening. From the
Okay. Yeah, but I don't quite understand. So, do you think that the data at null infinity is sufficient to reconstruct your Weidmann function in the bulk?
So this is the point. It should not, because it will miss every bit of information that was in the original initial data surface and went down through the horizon. So he don't collect complete information about the quantum state. So this is why I say this is a bold proposal, in the sense that it might need a lot of tweaking to turn out in an actual idea. But the central point would be to try to answer the question, how well can that person describe what was happening?
Okay.
Provided he don't know about anything that went down the horizon. So of course, he will not be able to, that person will not never be able to reconstruct the Weidmann function, the Weidmann function that we begin with. And of course, this will not be the case.
Yeah, okay, good. Then perhaps a question not directly related to your talk. So you computed correlations and predominantly in the exterior, but also between exterior and interior. Now, do you think that your method will also be able, with your method, you would also be able to compute correlations within the black hole, in particular near the singularity?
Okay, so I will tell you about some preliminary results that I have. So as far as we go down to 0.76, which ends up being the closer to the horizon we have produced data for, we could go closer, even closer, but then I will not be able to anticipate how well things will go. But as far as we get down to 0.76, things should be fine with both points inside the horizon. I have done a preliminary calculation and it seems to work. But as I'm saying, it is a preliminary calculation. So it should be better explored to see if everything is actually working well. In principle, it's possible.
Okay, because I wonder, because with Christiane Klein, we did such a calculation in near the Cauchy horizon of, say, Reisel-Nordström black hole, and we saw that there seemed to be long-range correlations. So I wonder whether you could see a similar effect here near the singularity of Schwarzschild or not.
Okay, so this is an interesting point, and this will be an interesting thing to do, and I think it will be, given the data that we have and everything, I think it will be fairly fast to perform this exploration in Schwarzschild and compare with your results.
Okay. Good. Yeah, thanks a lot. I think I'm done for the time being.
Okay. Thank you, Jochen, for your considerations and also for your suggestions. I mean, a couple of months ago, when informal talks with Mark, you gave a couple of ideas that were good to explore.
Well, yeah, honestly, I think in your discussion with these in and up contributions, I think you would profit a lot by having a look at the propagation of singularity theorem, because essentially everything you are talking about there just follows from that.
Yeah.
So I think that may be useful to get a simple understanding of what's going on there. Yes.
I see.
Yeah. Okay. Good. Then I'll pass over the microphone to the next person. Thank you.
So thank you very much, Johan, for a thorough questioning. Yeah, okay. So I'm omitting making comments. I'm just letting João answer the questions from the committee. If anything, we can discuss a little bit later. So I'll just move on to the next one. If my geography is not wrong, Fabri from Valencia is the next one online. So you can start whenever you wish, Sandro.
Okay. Do you hear me?
Loud and clear.
Very good. So first of all, I worked quite a bit on correlations in one dimensions. So a lot of, many things are analytical. And I was hoping that someone will do the difficult job to do this in 3+1 dimensions, which is extremely more difficult. And I'm very happy that you did it. I don't do numerics, so I was a bit afraid to look at the manuscript. I must say it is written very clearly and very honest. So very happy to be here, to have read it, and also to have heard your very nice presentation.
Thanks.
So
Thanks,
not being numerics, a few of my questions are, I'm for sure, very naive. So let me start with something which is probably very naive for you. You always go, so in computing the correlation, you consider 2 points, 6 prime, with an angular distance, p over mostly. Can you tell me why p over 3, why it is important to have it?
Okay, so in the very big, this was a decision that we took in the very beginning because, as I pointed, we didn't know if our method would work well on caustics too, at the very beginning of the work. It ended up working, but we didn't know it beforehand. And then we just decided to, at that stage, let's take an angular separation between the 2 points so as to avoid caustics, because we know it works when not on caustics. And then we have done all the explorations using this angular separation of pi over 3, but we could use any other angular separation, I presume, and it should work equally well. In particular, we can also do with gamma equals pi, for instance, which should be fine, provided that now we know we seem to have things working on caustics. However, gamma equals 0 might be a trouble because this will include the coincidence limit, and our method, unfortunately, don't work in that limit.
Yes, you said. Okay, very good. Now, sum over L, which is another tough problem. From what I understand, you've been able to produce reliable results until L equal to 44, and then no. But in practice, how many L do you need to get a reliable result?
Okay, at some stage during the course of the work, I have done the L sum up to varying values of L. So I have done it to L equals 1, 2, 3, just to see how things are going. And I can give you a rough view that, at least at a visual level, the plots stop to change past L equals to 40 visually.
Yes.
So and in effect, we are only considering up to L equals 12, then it's killed exponentially. But I would say that L equals 100 might be an exaggeration, and we might be able to reproduce our results going to a lower value of L. Although I would not be sure about how that would affect the final precision of the results. And the L equals 12 thing was done in order to obtain at least 2 correct digits. So the L equals 12 mode, it is produced with 2 correct significant digits. So everything should be precise up to 2 significant digits. And this is a very conservative approach, okay? Because the L equals 12 has much less significant digits than the L equals 0 and 1 and so on, that converges much faster.
Yes, but when you sum all these contributions, you mean up to 12 or up to more than 12, which are the most important ones? You really have to go until 12 or to 40, or which are those that give the main contributions?
Well, the rule of thumb is smaller L, larger contributions. And then the larger one gives smaller contributions. That would be the rule to use.
But 3, 4, 5 is you need more than that.
Yeah,
Stop.
three, yeah,
Three,
yeah,
four,
three.
it's not enough.
No, it will not be enough. And I also should point that naively we might think that, okay, let me go to L equals 1,000,000 because then I have that precise, the deadly precise results, and this is not true because then we start to have a lot of oscillations near the singularities of the Whiteman function, which are to be related with Gibbs phenomenon.
Yes, can you say something about the Gibbs phenomenon? I'm not sure it is included in the text, or maybe you did, and I overlooked it.
So I included a very brief comment on the text where I pointed that if we include too many L modes, then we will end up enhancing oscillations that happen near the discontinuities, near the singularities of the Whiteman function, which are something that we attribute to Gibbs phenomenon. So this is as far as I go into the Gibbs phenomenon in the text of the thesis. So there is a balance. I mean, you don't want to include too much modes in order not to have these spurious oscillations. However, if you include too small number of modes, you'll then end up losing a lot of the, say, small scale structure, because a singularity is something that happens over a very small scale. So if you don't include sufficient modes, that singularity will be so smoothed out that you might not be able to see it, for instance. So it will distort the final result. Then there is a fine tuning that should be performed.
But yeah, so I understand that to get a reliable result, to come back to the previous question, you need quite a bit of L modes. Otherwise, the result is not reliable. Okay.
On top of the smoothing.
Yeah. On top of the
smoothing function that we use.
Yes.
We need both things.
Yes. When you analyze the behavior of the Whiteman function for Bulwer, Harter-Hawking, and Unruh outside the horizon, you say that generically the first is bigger than the second and bigger than the third. So the Bulwer state Whiteman function is the one that has more correlations, no?
Yeah.
And
yes.
You make a similar statement, not for Bulwer because it doesn't apply, for Harter-Hawking and Unruh across the horizon?
I don't remember if I made a similar statement, or if I made the explicit comparison to make that statement, but I believe I would be surprised if the Harter-Hawking state ends up being smaller than the Unruh state. Let me see if I have something here. I think I do. Outside. No, I haven't included it, unfortunately, but there is a plot of correlations across the horizon where I do a linear plot with both the Unruh state and the Harter-Hawking state, and it's a plot where I analyze the decaying behavior. It's in the thesis, but I haven't included it here, unfortunately. And we will be able to answer that question by looking at the plot.
What you remember? Which figure is it?
Just give me a second. I think I have it. I think I have it at the end again.
Okay.
No, this is for both. This is for both points outside. Okay, I don't have the figure. I was confusing with this one, but this one was for both points outside. So this is something I have to do in order to give you an answer. So, but in principle, I would be surprised if the Harter-Hawking presented more correlations than the Unruh. But this is, I guess, without.
Yeah, so I have worked well in the 1+1D context, of course, for the Unruh state, but I never looked at the Harter-Hawking, so I really don't know what to think about it. Okay. Although in 1+1 dimension, it is very simple. Okay. You said that the Weidmann function for Unruh and Hartle-Hawking, when the 2 points are outside the horizon, they have a non-trivial structure. There is a peak, you said, no?
Yeah, let me go
I
back to
don't
the
know
slide.
what this is because I would not expect it.
This was a surprise for us too, because I mean, because of your papers. So we were looking
Well,
at
but
it.
our papers are far simpler than this analysis.
So yeah, here it is. Now I have to say
What is
that
this delta t? What is t? T is Schwarzschild? Delta t equal to 0, you said.
delta t is the t coordinate, the usual t coordinate.
Schwarzschild t coordinate, no?
Sure.
Okay. Yeah, so I have no idea what this could be. It is always u prime equal to u. Isn't this just the... No. It's not coincidence limit, no? No, this is not coincidence limit.
No, because of the angular separation.
Okay.
And notice that we are not looking at the full Weidmann function. I'm taking the Weidmann function and subtracting it from the Bower state Weidmann function, which we know that contains no radiation. So this is the difference between Hartle-Hawking and Bower, Unruh
Yeah,
and
but
Bower.
what would be the interpretation of this? Because in practice, you're looking when the 2 points are outside the horizon. Say you have 2 Hawking particles, u and u prime, and you have a peak when u equal to u prime. So it's I don't know. Do you expect this feature to appear also if you take derivatives or construct density correlator, all this type of stuff?
Yeah, because wait, across the horizon, yes.
No, I'm talking about outside because it's something
outside. I think this will happen. Let me explain to you why I would expect it. So I will use the in a linear scale plot, we see a local maximum. So naively, taking the derivative of a local maximum, we produce a 0 and 2 other peaks.
Yes.
So that's a very naive way of thinking, but based on that naive assumption, I would expect the derivatives to also show interesting things. So this is
Okay.
something I want to do.
This is a potentially interesting thing. Yeah. Okay. Okay. Let's go to across the horizon then.
Okay.
So again, in 1 plus 1D, you write down the 2-point function in Schwarzschild, you don't see anything. It means that in your computation, if you take the limit where the effective potential goes to 0, everything disappears, no? All these non-trivial structures should disappear.
Naively, yes, but yes. Let me give a better statement. Here we see the non-trivial structure propagating away from the horizon. But if you note, the structure is dwindling in size as we move away from the horizon. So I would expect that as we move towards infinity, it will dwindle more and more and eventually become invisible. So this would be my expectation based on what I'm seeing here.
Yeah, no, my question was if we artificially removed all the effective potential, all these things should disappear because we don't see it, because artificially removing the effective potential means it's a 1 plus 1D computation, no?
Yeah, but
Yes.
By artificially removing the effective potential, wouldn't we end up changing all the mode solutions on everything?
Well, we basically all transmission coefficients are 1, all reflection coefficients are 0. So in a sense.
Okay.
Nevertheless, in 1 plus 1D, when you took derivatives and construct the density-density correlation, it doesn't just mean that you take derivatives of 2-point function, but you divide it by 1 over f and f prime. F is 1 minus 2 m over r. To this prefactor here play an important role,
Mm-hmm.
at least in acoustic black holes. In Schwarzschild, if you do 2-point function at equal time, you still don't see anything, but unequal time, yes. So again, what do? We consider the 2-point function either at equal time. For us, equal time is Pahnlevé-Guldstrand, but you can do equal time Eddington-Finkelstein V, which is basically the same thing.
Mm-hmm.
Or unequal, so equal to different from V prime. So the 1 + 1 dimensional results for Schwarzschild change, because when the 2 points are at unequal time, you can have correlation which you don't see when V equal to V prime. But coming back to this, there is not, you're not computing, not yet at least, computing this more complicated structure. So I would guess that all this non-trivial feature, which I believe, which is very nice,
Mm-hmm.
it has to do with the effective potential and is probably related to Hawking radiation. And it is very nice to see that it appears here at this level. Let me comment on the fact that usually, say again, I'm talking about the density correlator. From the density correlator, usually we expect 2 non-trivial features for points across the horizon.
Mm-hmm.
One related to Hawking, so U and U prime, and another related to just best scattering, which is a U and a V, U V prime or U prime V. I don't know how you know.
Mm-hmm.
Of which one is positive, the other is negative. So here you don't just see one minimum, no?
Here,
It's one minimum traveling to the right.
yeah, we see one minimum traveling to the right.
No other feature appears, no?
Other than that, there is just this steppish behavior, but I don't think it will apply. But naively, but again, using that naive thinking, if we take the derivative of this quantity with respect to V primed,
Yes.
right at the center of the step,
Yes.
so close to U equals to minus U primed, I would expect a peak, but a negative one, then a 0, and then another smaller peak, which should be positive.
Positive?
Yeah, a positive one.
This is what we expect on the density correlator. But yeah.
So maybe we are going to see all that.
And also you have you have in principle the right it is situated the right spot U equal to minus U bar in your which is what we expected. So yeah, so this is nice. I think these are nice results, and I think nobody did it. And it's not unexpected that in 3 + 1D you see these features already in 3 + 1 dimensions.
Mm-hmm.
So far, very good. Yes, again, you said we might see a negative and a positive peak when you take derivatives. If you construct some density correlator, it is important to take into account this prefactor 1 or FF prime, because this will modify in principle the behavior close to the horizon. So it will be very interesting to see the results of these quantities starting from this.
I see, and I'm looking forward to do that.
About the omega delta contribution, which is made of psi ins and psi up. If you go back to the expression of the Whiteman function for Unruh and Arco-Hawking for points across the horizon, yes. So the last term in the third line is the one that you select. But in the second line, there are also the terms in. But the terms in the second line are also psi ins, psi up, psi ins, psi up. No, what is the difference between those? Why did you select just the last one and not those in the second line?
Well, the reason was essentially because these two terms they are they are genuinely quantum in the sense that they are already at the level of the integrand, a contribution to the real part of the Whiteman, which encodes the state dependence.
Yes.
And it's shared across these two terms. Other than that, it is related to the fact that when we rewrite this in terms of the Eddington-Finkelstein modes, this last term, it ends up being a combination of a mode that has support only outside and another mode that has support only inside. In that sense, it is different from the other terms.
But the terms in the second line, you have a psi in and a psi up. In which sense this term is different from the other one?
Well, okay, looking here at the level of the first sense in which it would be different is because the last term is the real part of this thing. Here we don't have this enough symmetry to state that we have the real part. So this will be in general a complex valued terms.
Yes.
And well, there is the difference that here we have an exponential of omega, here an exponential of minus omega.
Yes.
So the combination is similar, but the overall behavior should be different. In fact, I don't remember now if I included in the thesis or not, but I do have results for each of these terms separately.
Okay. I didn't see them.
And I didn't remember if I included in the thesis, but in fact, we verified that the only one that has, say, that non-trivial behavior, that special behavior, is this last one, which is what caught our attention.
Okay. And which has, I think you've shown that it has the most important features, no?
Yeah.
Okay. Okay, very good. Not much is left. When you're talking about, you've been discussing, well, this is something I know much less, non-light crossing singularities in the Whiteman function. You discover them in the ingoing and outgoing components, but when you sum, they disappear.
Yeah.
So is there a general argument why they should not be there?
If there is a general argument as for why it should not be there, assuming that these are singularities, at least they would be at least unexpected, because we know that a singularity appears only when the 2 points are connected by a geodesic, and these unexpected ones that we have found appears when 2 points are not connected by a geodesic. So they would be at least unexpected. So
but magically, when you sum up everything, they disappear, no?
Yeah, there must be, yeah. No, not exactly magically, but there must be a deeper explanation, which we don't have up to this point, that should be related to the nature of these singularities, or to what causes them. We haven't been able yet to pinpoint where are they coming from, what are they. We just know that they seem to be singularities, so we conjecture that. They have a fourfold structure, just like the light crossing singularities do. And so far, this is what we know. And of course, that they cancel out when we sum both terms. So this is something that don't appear in the final complete Whiteman function.
Okay, if you just go to the last page of your presentation. No, it's not in the conclusion. When you said the conclusion and the final consider.
Here.
When you say, okay, future work then, sorry. Yes. So I wanted to ask you, what do you think about the last point, harvesting across the horizon? Is it something interesting?
Well, there are papers exploring harvesting across the horizon in 1+1D. And the current conclusion is that in 1+1D, it is possible to harvest entanglement across the horizon in specific setups. But in 3+1D, we have a very different geometrical structure, which can produce unexpected results, as we have seen, for instance, for harvesting for time-like connected detectors. So now we are curious to see how the geometry will play a role in the 3+1D situation. And it will also be interesting to know that a detector inside and a detector outside, they can become entangled, because these two detectors, they can't communicate with one another. So it would be a very interesting result to explore and have and understand, because it might relate in a deep way with Hawking radiation.
Yeah, this is why it's probably interesting from this point of view. Yeah. And yeah, so the last thing, but you have already commented, would be nice to have results for the 2-point function when the 2 points are inside the horizon. You said you have already started to. And also to produce something like density correlators and all this type of stuff. So I'm looking forward to see results about that.
Oh, great.
So I finish it, and thank you very much. Nice work.
Thank you, Sandro. Nice to have you here.
Indeed, thank you very much, Sandro, as a world expert in this sort of specific calculations. So we move on now to Brazil. So the next one will be George Matzes from Unesp in Sao Paulo. So George, whenever you wish.
So thank you very much for the invitation. So I was promoted from spare to full panel member a couple of years ago. So I didn't have enough time, I would say, to read thoroughly the thesis, but still I could, I think, assess it enough to say that it fulfills all requirements to be accepted as a PhD thesis, first of all. And it analyzed an interesting issue, that is quantum field theory correlations in curved spacetimes and how they can be harvested. And this is, I think, very interesting. Concerning the thesis, I think it's comprehensive and very well written. I only missed, if I could say something, some more discussion on caustic and caustics and cusp singularities. I was not that familiar, so I think I would appreciate even more your thesis. But don't take it as a criticism, since we can see it as my fault. Okay, my loss of knowledge about basic things. So I would like just to clarify one point in the previous discussion and cover another one that was not covered yet. So I would like to see if I understood the discussion on harvesting and communication. So let me say how I understand it, and you correct me, okay, if I am wrong. Okay. So you begin stating correctly that quantum fields are entangled, and you begin with detectors that are switched on in a non-entangled way, right? In the beginning. Okay, good. So this is the first step. Now, as time goes, the detectors entangle with each other through the quantum field, so the whole system gets entangled, even when they are causally disconnected. Right? Okay. So if I understood correctly what you write in your thesis, then any entanglement that comes out in the system field plus detectors, before the detectors get causally connected, would have nothing to do with communication, in the sense that although they would be entangled, the whole system would be entangled, you would not be able to pass information from one detector to the other detector through this entanglement. Is it correct?
Yes.
Okay. Would you like to comment anything about that? Or
no, this is the correct picture. Space-like connected detectors, they can't communicate by definition of space-like separation. So any entanglement they acquired must be some entanglement that was already on the field.
Okay, good. So I think I understood that part. So my second question is something that was not covered, and I would like you to elaborate a little bit more on this. And actually, it's a twofold question.
Mm-hmm.
And it's related, you begin motivating your thesis talking about this so-called information loss in black holes.
Mm-hmm.
And you also comment this at the end, although this is only used as a motivation, right?
Mm-hmm.
So my first question is whether you see any paradox in the loss of information in black holes, whether, in your opinion, this deserves the qualifying of paradoxical.
Well, a couple of years ago, when we met for the first time, I believed it was a paradox, but as of now, I don't really see it as a paradox anymore. So I just adopted the name puzzle because some people say that it is, some people say that there is no paradox. So I
In
just
your
call it a
opinion,
puzzle.
why this would be a puzzle?
It's a puzzle because nevertheless, independently of the fact of being a paradox or not, it's a puzzle because I believe that the disagreement between the two schools, one that believes that there is a paradox and one that believes that it isn't, might be related to the fact that maybe we don't understand completely how information is distributed and how information flows throughout the space-time. And there might be, by exploring this issue, by exploring these correlations, we might be able to finally convince everyone that there is no paradox in principle.
Do you think this is paradoxical, the fact that you begin with a pure state and after evaporation, assuming that the black hole completely evaporates, you end up with a mixed state? Do you see this as a paradoxical or as a puzzle?
To be honest, no. It puzzled me before, but it's something simple. What happens is just that information got filtered to infinity, and the black hole isn't there anymore, and that's it. So I don't see.
Good.
I was surprised by it at first when we first talked about it, but now I'm not that surprised anymore. I can even say that I'm not interested in actually exploring the paradox anymore. But I know that my work might be used by people who explore the paradox to give an argument. I don't know what can they think about it.
This is my second question. So everything you do here is assuming a background, a globally hyperbolic space-time, right?
Mm-hmm.
Okay. So how can, in a globally hyperbolic space-time, information is by definition preserved?
Mm-hmm.
Right. Why this work could be used, even assuming that for some reason people still see any puzzle, although the singularity opens the system. And so when you trace out, this is as a usual quantum mechanical system, open quantum mechanical system, you trace out these degrees of freedom. So there is no puzzle at all about, information. Well, you have, singularity destroys information. So, but even for those, let's assume that people who want to force, or let's assume that people assume that quantum gravity is going to solve what we in general relativity call singularities, right? Making the space-time globally hyperbolic. So why, I don't see really why this kind of analysis can shed any light about the destruction of information by black holes that ends up being, what people don't like about the loss of information in black holes. So you are in a global hyperbolic space-time. So would you like to say some words about that?
Well, when it comes, if someone hopes to see in my work any light, assuming that there exists a quantum theory of gravity, then they will not see anything here, because I use the semi-classical approach, which doesn't even consider, I don't even consider back reaction. So the maximum, I think that the most that someone might try to extract from my work is maybe to say that, look, there is information encoded in Hawking radiation, as you can see that there is this non-trivial behavior in correlations across the horizon, and for this reason maybe the Hawking radiation might be able to carry information and so on. So the kind of thing people who believes it is a paradox would say, that Hawking radiation carries information away, but they don't know how, they don't know the mechanism through which this would happen. Maybe this person might see some light in my work, but by no means it will shed light on a full theory of quantum gravity, because I'm using a semi-classical framework, not even considering back reaction.
Yeah. So let me there say that that I really don't think that anybody should, you are in a pure state. You evolve in this pure state. Pure state is going to pure state. So correlations from inside the black hole is expected, unless information is traced over because it's destroyed by the singularity. Right? So this is not surprising that you have correlations inside and outside. This is very much different from saying that information from inside goes outside. Right? So I would just mention that I don't see, first of all, any puzzle about the destruction of information by black holes. Nothing to be resolved, actually. Nothing to be resolved. Whether or not quantum gravity is going to change the Penrose diagram of evaporating black hole and make the whole space-time globally hyperbolic in such a way that you don't have any loss of information, this is another story. This is a story, right, related to quantum gravity, but not to semi-classical gravity, and still, this is an article of faith that quantum gravity is going to resolve black hole singularities, right? It might not. Right? Okay. And also, I think that all this discussion is very, very interesting. Very, very interesting. But still, it's not going to shed any light to any so-called black hole information loss. Just a lateral comment that has nothing to do. I mean, it doesn't take any, your thesis is very, very nice, very, very interesting, and it doesn't need this comment about black hole information to be motivated. Okay?
I see. Okay.
Okay. So I am very happy to be promoted from spare to full member. I still expect to have time to read your thesis more in more detail. And I thank you very much, you guys, for inviting me. And congratulations for you and for your supervisor for this very nice work.
So thank you, George. It means a lot for me to have you here. Well, let's have a pizza at some time when I'm in São Paulo.
Good. Good.
Thank you for your comments.
Yeah, thank you very much, George, as one of the world experts on quantum field theory and gauge space-time, and I'm happy as well that you were a full member of the committee. So last but not least, local UFRJ Rio de Janeiro, Carlos Aro. Carlos, you can start whenever you wish.
I would like to thank Mark and João for inviting me to this very nice thesis that I've learned a lot, I've enjoyed a lot. And also a comment that that's not related. It's related to the last thing that João told us, that São Paulo has the best pizzas in the world. I think it's not a disputable question. It's a nature, it's a law of nature, I think. Only a joke. And I really enjoy these theses. Many of the questions, I'd like to thank the jury. I learned something. I came to think something after your remarks and after your questions. And my questions will be, I'm not a specialist in this numerical stuff, and I become delighted. I have some few questions. Many of them are just my curiosity. And the first one is that I know that I think Wald demonstrated that the nature of the singularities of the Whiteman functions. Then you told me that I think it's a paper from Booz and Mark. They showed that there is a two when it forms a caustic, and I reinforce Professor Max's comment that to me it was very difficult to see after the very beautiful. I understand you simulate the wave front, and then it forms a caustic. I have only a naive idea what the caustic is, what's formed numerically, and what's the imprints. That's why I'd like to see there. It's only a comment. And then that structure of the fourfold, when there is a change of type, of singularity type, for the real type after the first caustic, it becomes a imaginary type singularity, and so on. It was analytical discovery. It was discovered only after this paper of Claudia Booz and Marc Casals, or it's a fairly known fact.
Well, let me tell you the history that I know. So we know that there is a singularity. Let me go back to the slide just a second. Okay, we know that the singularities appear, and this is a theorem. As far as I know, this theorem is in books by Ikawa and Garabedian, which shows that there is a singularity.
That's mathematical stuff, and they work with a curved space-time, Riemann general manifold, or not?
Well, I haven't went to the books to see the proofs and everything, but I believe they consider a generic setup. Maybe, well, Mark can shed the light on it, because as far as I know, there is a theorem that is proven in that book. Then there is the work by Casals and Nolan. In that work, Casals and Nolan, they actually show analytically the singularity structure. They make the whole calculations from end to end and show how the singularities look. But if I'm not misremembering, they do that for the retarded green function. Mark can, if I'm missing, Mark can correct. So the shape of the singularities, it was derived analytically, even on caustics. But on caustics, the expressions are not as insightful as these ones. So I haven't included them here, but they are on the paper. What Claudia, Buzz, and Mark have done in 2018 was to show that even the real part of the Whiteman function, which is not related to the green function, presented this fourfold singularity structure. So they exposed for the first time, but they already knew what was expected to be.
Many thanks. I have another question. It's about a numerical one. You relied on what you call the data set about the inputs that you. What are your your data in this case?
Okay.
To simplify, and
I have a slide with it here. Let me recover it in a second. Okay, so I have two slides about it. Now, what is on my data set? So a lot of radial modes. We have varied the frequencies from 10 to minus 3 up to 10, so 10,000 points. For each frequency, we varied the L from 0 to 100, so 2 to the second times 10,000. And we have done that for each of these radiuses. If I can remember, in the end there were 100 and something radial points. So we are dealing with a huge amount of data, not only for the solutions but also for the first derivatives. So this is what composes our data set. To evaluate each of the solutions, the ingoing, upgoing, and inside, we used a different technique. The Jaffe series is a very fast conversion series, which we use outside the horizon. For the upgoing mode, which is our current bottleneck, say, in precision, we have to use the numerical method implemented in the black hole perturbation toolkit, which is a Mathematica package that is also available in other programming languages. Inside the horizon, we used the usual Frobenius series. And as a result, we got this precision. So the ingoing modes are good to 20 significant digits, which is great. The inside to 16, which is great. And this is throughout all the space of parameters. Only the upgoing modes, that they are less precise. We got them to 9 significant digits and within this range of L. However, this isn't such a trouble because we are smoothing out L larger than 20. So in the end, the unprecise upgoing modes contributes with almost nothing in the end. For the coefficients, we had to do some work too, because while Buzz and Casals in their paper in 2018 evaluated the transmission ones, they haven't evaluated the reflection ones. I don't know if they haven't or if it was just not saved on the data set. So I used their transmission coefficients to derive the incidence coefficient normalized by transmission. So just take one over transmission. For the reflection coefficients, I had to evaluate the Wronskian using our numerical data for the modes and derivatives. And this took a lot of time, but in the end, everything is self-consistent to 9 significant digits. And this is what composes our data set. Roughly, I think we are dealing with something like 80 gigabytes of data.
many thanks, João. I think you have clarified my point. I will ask you after. And now another naive question about this. Your Mathematica data set that you have obtained for the first time, is that common from your subject to be at a kind of GitHub to another NA student can follow it, can study it, or it's something only?
I think it varies a lot from person to person. There are some people who publish the data set on open sites like GitHub for everyone to use. And I kind of want to do that, but I would talk to Mark first, because I think that I think I can do it. I just have to talk to Mark first to know if it is a good idea and everything. I just have to figure it out, because I'm a very young researcher, say I'm not that mature. So I don't know how these things work, but I have seen people, especially from high energy physics, doing this kind of thing.
And thanks, you have also clarified my curiosity about it. And the other thing, I think Professor Alessandro Fabri, and he already pointed out, and it's about the Whiteman function delta, the same I was that curious because there are other terms that are present in other two, one,
Mm-hmm. Let me.
and they are the same, and you have chosen only the real part and these, the upgoing and the ingoing sector. So I was thinking that it comes purely from the rocking radiation or something else. However, I think I mistook that point, as misunderstood that point.
So
Because there are other terms that are
Mhm.
present in both of them.
So what happens is that, okay, the reason for me to pick this last term was the reason I pointed. So when we try to trace where this term came from, we end up concluding that it came from a product between a mode that has support only inside the horizon and a mode that has support only outside the horizon. So this is the only term presenting this specific behavior, because for the other terms we have, for instance, ingoing modes, and the ingoing mode, it also has support inside the horizon. On top of, beyond this motivation, there is also the fact that we have actually evaluated each of these terms separately, and then we sum all of them to compose the full Weikman function. What we have noticed is that it is this last term, which is a common term between the Hartle-Hawking and Unruh states, and which is a purely real term. So let me refer to it as genuinely contribution from the state, which produces the non-trivial behavior that we became interested in. So it was for that reason. So this is the one that produces the interesting behavior. I'm not sure, again, if I included in the thesis the contribution from each term separately, but I have verified it, and the good behavior come from this one, the non-trivial behavior.
And many thanks, João. And my last comment will be on the chapter 6, when you talk about the Unruh with detectors, and it has a very beautiful, a very good review of Professor Matzes. It was very nice review, and your review of these very difficult things like entanglement and also by this Unruh with detector, I think it is lacking, but it's not. I know that's only. It's not important. However, I think the diseases must be studied by a student. So it's very good to have the things, especially in sections 6.1, 6.2, and 6.3. And another question that I like to, why did you use the negativity and not the concurrence or entropy of formation? And is that how it's only a computation stuff, or there is a more deep?
Well, there is the entanglement entropy is the most, say, common one or the most famous one, but we can only use it when we have pure states, and we have no guarantee that the joint state of the detectors at the end of the experiment will be a pure state. So this rules out entanglement entropy. Then we have other choices. Why choosing the negativity? Because, well, in this kind of setup, we already know how to work with it. We know it's possible, it's doable numerically, and it has been widely explored in flat spacetime. This is the practical reason. So not to use the entanglement entropy, which is the most famous and, well, at least for me, the most intuitive one. It's because we don't know if it will be a pure state in the end. It might be, it might not. And the choice of negativity is for a practical reason. We want to quantify precisely entanglement, and we want to quantify entanglement in a state that might not be pure. So the negativity does the job.
Negativity and also concurrence could do this job. And Dave asked you how this occurs, and I think I'm very glad to be here, to be part in this panel, to discuss this. I really enjoyed reading your thesis. I think, like Professor Alessandro, Professor Zan told us, that it is a very honest, although heavy stuff, especially in the numerical part. It takes me lots of time and it starts smoking my head. It's very difficult to me. I know that you have learned a lot, new techniques, and I think I finish my questions here. Thank you, Mark. Thank you, João.
Thanks, Carlos, for being here, for accepting, and for all the comments.
Indeed, thank you very much, Carlos, for your participation in the committee. So we've reached the end of the questioning part. So I believe now the committee should gather separately and deliberate about this. So, Larissa,
Sim,
já terminamos a parte das perguntas.
sim, eu vou abrir a sala simultânea para vocês, é só aceitar na tela de vocês, tá bom?
Ok. Todos nós, exceto o João, certo?
Isso.
Ok, obrigado. So, Johan and Sandra, Okay, so I think we're all here. Okay, so we've discussed all of us, and I'm extremely delighted to say that you passed and you've got a PhD, João. So
Gee. Thank you.
many congratulations.
Oh, thank you.
Congratulations.
To both.
João, I will send you this thesis with the small typos, corrections, and reference and all that.
I appreciate that.
So you have a deadline for providing the final version?
Now, I don't know how it works. This is something I have to ask Larissa.
3
In ja-
meses. Em 3
Ah,
meses.
3 months, Sandro.
Which day?
3 months.
3 months from now. Okay.
Larissa, o que nós fazemos agora? O que nós temos que assinar?
É só a ata e a folha de rosto, mas eu vou enviar por e-mail para vocês explicando tudo direitinho, tá?
Ok.
In English for me, sorry, huh?
Isso.
Yeah. So, she's going to. Yeah. Okay. So you understood her Portuguese, right? Did you understand? She's saying that she's going to email us whatever.
No, but I guessed it.
Okay.
there are 2 pages that you must sign.
Okay.
One is
Okay.
And it will be electronic. Okay. She will send me the instruction. I will follow them, I hope.
Larissa, o Johan não vai conseguir assinar durante até 2 semanas. Tá tudo ok?
Ok.
Ok, obrigado.